surely convergence, which was actually the strongest one. Okay? You understand? You still don't get the difference. I mean, you kind of wonder why. Okay, so why is if it happens with probability 1, then why it's just
almost.
Yeah, so almost surely. And the reason for that is because there are some events, for instance, that happen with probability 1, although they quite not be intuitive that they can occur. For instance, I'm not sure if you got a.
Yeah, no, I was just wondering, is it possible to prove that events are happening with the probability 1, or is it not possible?
I mean, it is. I mean, guys, maybe we talked about, one famous example is the geometrical distribution. Okay? So that was an example that I already considered. Okay? So where you have, actually an experiment, okay, so where you calculate the number of failed trials, okay, so X is going to be the number of failed trials, okay, so the random variable, so X is going to be the number of failed trials. Okay? You understand? And you stop the experiment until a certain event happens, okay, so for instance, you throw the dice, and you stop it, basically, and when you get the number 6, you stop the experiment. Okay, and you count the number of failed trials. So, for instance, if you throw the dice and you get 6, just right away, with, let's say, with success probability P, all right, then you have 0 failed trial. Okay, and the probability is 1 minus P that this is not going to happen. Okay, and that goes on. We already talked about it. Okay. All right. Now I have shown you guys that the probability that X is finite. So this means that sooner or later, the experiment stops. You don't know when, but sooner or later, all right, I've shown you that this is going to be equal to 1. Okay? But does that mean that it's gonna stop from the theoretical perspective, or maybe you can see this from the practical perspective. So from the practical perspective, there is a possibility that you sit down, you throw the dice, you throw it, and you do not get 6, right? I'm not talking about the fact that this is not likely. I mean, it's not likely to happen, right? But from the theoretical perspective, there is a possibility for that. Now, what would be the probability of that? Okay, so we assign, the problem is that we have to, although that can be possible, we have to assign actually the probability of that event to be equal to 0. You understand? Okay, so but although it's going to be 0, it doesn't mean that it could not possibly happen. You understand? Because you can, you sit down and you throw the dice and you throw the dice and you throw the dice and nothing happens, and then you you grow old and you lose your hair and stuff like that, and and whatever, and then you still don't get the number 6, right? Because at each trial the success probability stays the same, right?
Yes. So almost means.
So almost, that means that you can say that here that this experiment terminates almost surely. Okay, so the experiment. Okay, so the experiment terminates almost surely. Okay?
So it's like practically it terminates because there's no example where it never terminated.
Why?
But because
is there, from a theoretical perspective,
yes,
is there no possibility that the experiment doesn't stop? Let's say we play a game, we play a game and you throw the dice and I throw the dice, and if your number is bigger than mine, then I pay you something, and if your number is bigger than if my number is bigger than yours, then you give me some money, right? And the question is, what would be the probability that one of us goes bankrupt during that experiment? I don't know how much money you have, but it doesn't matter. Okay? So let's say you have like $1 billion or something. It doesn't matter. So you're like kind of Donald Trump or whatever. It doesn't matter. Okay, so sooner or later, one of us will go bankrupt. That is another example that I can show you here. I could show you here. So you can say that one of us, either you or me, gonna be bankrupt almost surely. But does that mean that from a theoretical perspective, that this is gonna be necessarily the case? I mean, think about it, okay? Maybe something happened like, you know, you win, I win, you win, I win, you win, I win. And this goes on and on and on and on, you know, until the sun stops shining. You know what I'm saying? So, you understand that?
Yeah.
Now the probability of that event will be equal to 0. But it could happen, right? And these are the limitations of probabilities, right? So we have to actually assign, let's say probabilities to a certain event that they're not going to happen. Or they could happen from a theoretical perspective, but they're not going to happen almost surely, let's say. Right? You understand? On the other hand, let's say you have a monkey, and this is a very, very famous, I forgot how to, this is a very mysterious theorem, I forgot the name of it, but there's a theorem, it's called, I think, the infinite monkey theorem or something like that. So it goes like this. So you have a monkey here, and he's typing something, okay? And the probability that you get a whole dictionary, you know, from A to Z, let's say Brockhaus, okay? From A to Z. So he'll get, you know, Brockhaus A to Z without any mistakes, stuff like that. It's going to be equal to 1. So the claim of the theorem will be that the monkey will, you know, sooner or later, with probability 1, you know, get, you know, the whole dictionary almost surely, basically. Okay? Now, is this going to happen? Are you going to observe that in your lifetime, that you have a monkey or an idiot, let's say you have an idiot, and he's typing, you know, something, and, you know, randomly, and, you know, and then sooner or later, he or she, you know, gets, you know, the whole dictionary from A to Z. Is this something that's going to happen? No, right? An idiot will never do this, right? Basically, all right? But what would be the probability of that event? The probability of that event is going to be equal to 1. So you understand the contradiction. So this is the limitation actually of probability theory. So it doesn't get it always right, basically. You understand? Because a monkey or an idiot or a pig or something will never do this. Okay? Right? Neither from a theoretical nor from a practical perspective. And that's what I'm talking about. The probability of that event will be equal to 1 given an infinite amount of time. Okay? Right? I mean, yeah. That's the thing. So we have to distinguish actually between events that happen almost surely and, you know, just surely, or so just almost surely and surely. Okay? You understand? Okay, guys. So, and let me summarize that. Okay, so because these are I mean the relations between these things. Okay, so almost sure convergence implies convergence in probability. Okay. All right, so this is going to be remarked, okay? So almost sure convergence implies convergence in probability, all right? And convergence in probability implies convergence in distribution. Okay? So basically almost sure convergence is the strongest one among these. Okay? So let's say for instance you have a sequence. Okay? So if a sequence, okay, so this is a statement that I would like to make here finally. So if you have a sequence, okay, that converges to the limit with probability. I mean, I'm not talking about probabilities here, so as n approaches infinity. Okay? Now this implies that it will converge to the limit also almost surely. Okay? So if it happens surely, let's say, then it will happen also almost surely. And almost sure convergence implies also convergence in distribution. And convergence in distribution convergence in probability. I mean, this is also true, but I forgot, you know, about convergence in probability. And convergence in probability implies also convergence in distribution. Okay? So this is a chain of, you know, these convergence expressions that you can see. And I use convergence of sequences to define convergence of functions, continuity of a function, uniform continuity, and what was the last one? Absolute continuity. Alright? So all I need is actually convergence of sequences. Right? So that's all that I need for that. Okay? But this is the chain. So actually convergence in distribution is the weakest form of convergence. Okay? Alright? Okay? Now that's actually chapter number 5. Okay, so there will be, of course, then as you will, you know, you prove that as well, right? So that convergence, almost sure convergence implies convergence in probability. Okay? So that's actually the second part. Okay? So I'm not going to talk about that anymore. This is going to, so that was actually chapter number 5, and chapter number 6 will be about integrals. Now guys, I don't want to start that chapter now. Basically, I would prefer to start that, you know, on Friday. Okay, so I hope you don't mind because I actually have 5 minutes left, so I have to hurry. Okay, so maybe if you have questions, then you can ask it now. Okay, I will be happy to answer them. Okay. Does everybody know? I mean, I think I talked to almost everybody. Okay, so then on Friday there will be the last session that I arranged. Okay, on Friday. So after that, you should actually somehow know, you know, what you're going to write about. So I hope that this is going to be clear then. But if you have questions, then please do not ask me to hesitate. And there will be some of you guys. I mean, I will give you, or I will send you, like, you know, 1 or 2 information about, you know, the topic if I find something interesting, like especially if you have topic number 10 where the proofs are, or actually the model or something like that. Okay, so keep that in mind, and in, let's say, in 2 or 3 weeks, I will, you know, get in touch with you about your seminar as well. Okay. All right, and yeah, and do not forget your 5th assignment. Okay. That's going to be, the deadline is Friday. Okay, guys. All right. Thank you very much.